everybody. So, we're going to talk a little bit about how we use Cassandra and a couple of the technologies to fuel a variety of solar clusters at a relatively large scale. So, a little bit about me. My name is Joseph Streeky. I am the manager of the search framework development. So we own deployment of servers in AWS and feeding and searching and all that fun stuff. This is Josh Smith. He's one of our database administrators, and he's specifically my Cassandra administrator. So a little bit about CareerBuilder as a company, for those of you who don't know. We deal in human capital solutions, let people find the candidates they want. We have more than 22 unique visitors every month. We have more than 3,000 employers post more than 1 million jobs per month on our main site. We have operational branches in the United States, Europe, Canada, and Asia. So in total, across both CareerBuilder and its acquisitions, we have presence in a total of 55 countries around the world. So let's talk a little bit about specifically search at CareerBuilder, which is what I'm concerned with. As I said, we have about 1 million jobs each month. We have 60 million searchable resumes in both the United States and abroad. We have about 5,000 search servers, right, so that's individual Solr nodes, across both our private data centers and AWS. We have thousands of uniquely dynamically generated search indexes. So when a customer creates a document, they decide at the time of feeding what that index is going to look like. Solr has a really powerful feature called dynamic fields, for those who are interested, which allows us to allow each document to look totally different from a different document. Though generally, we have shared types of documents in specific cores, just because it's a little easier from a management standpoint. We have about 1.5 billion search documents across all of our document sets, which really means that the Cassandra has about 3 billion total rows, because we store each document twice, and I'll talk about why we do that in a minute. And we get about 2 to 3 million searches an hour, that we spike up around 6 million searches an hour during our highest volume points. So just to give you guys kind of a visualization on what search powers on our site. Right, we power job search, resume search. We power our autocomplete with search. We do job and resume recommendations with search. We have some analytics products that make use of the faceting power of Solr to provide some really interesting insights for our customers. We have employer profile search through search. We have a compensation portal that goes through Solr. We have Recruitment Edge, which scrapes all of your profiles off of various places. All kinds of stuff. We also power all of our mobile sites. So all search that happens at CareerBuilder happens on Solr and happens through my stack. So let's talk a little bit about how we're set up. So when we were setting up our feeding platform, we had some specific requirements. We wanted to feed more than 1,000 documents a second. And that requirement came from the concept that we want to be able to refeed all of our resume corpus, which is about 60 million documents in a day. And so that was where we started. We ended up getting significantly higher performance than that, but that was like our initial boundary case. We wanted all of our components to be able to scale linearly. We were moving off of a SAN for doing our feeding, and the big problem with SANs is if you have $1 million SAN and you want a bigger SAN, your next option is a $2 million SAN, and that was not a particularly appealing investment for us. We wanted to be all of our resources to be highly available, because feeding is really core to what our business does, and we want it to be easily deployable to multiple locations, right? So we want it to be easily deployable to our private data center and then out to AWS when we move there. We're kind of in the process of transitioning a lot of our resources out into Amazon as we speak. So here are some of the technologies that power our feeding stack. We make use of Sinatra and Ruby on top of Nginx as a very small web app to power all this logic. We make use of Cassandra as our data store, RabbitMQ as our queuing infrastructure, Solr as a search engine. We use our proprietary monolithic platform that's kind of in the process of going away that we call the Matrix, and it's full of all kinds of horrible puns for our batch processing, which I'll talk about. So to kind of give you a visualization of how our process works, right? We get data from sources like SQL and Hadoop. They come into our feeding stack. The feeding stack, which is in essence Sinatra, writes to Cassandra, writes to Rabbit. Then we have a processing tier that is watching the RabbitMQ, and as soon as it sees the message, picks it up and works it. We go through a couple different stages, which I'll talk about in a minute, that allow us to kind of fully transform the data and then route it to the correct storage. So we have, these are our feeding steps, to give you guys an idea of kind of the process we go through. We initially do content creation, so when we get in the document, it's in a application level format, and we transform it into a format that Solr can understand. Today we post to Solr using XML. It then goes on to a sharding step. During the sharding step, we decide where the document's going to be routed to. There are a couple different approaches we take to routing. On some of our bigger clusters, we have all of our searches distributed across multiple shards. So we have to always route the same document to the same shard, otherwise you run all kinds of weird problems in Solr. So that's one of the possible sharding strategies that we make use of. Another one is we created kind of like a minified version of some of the features that Solr Cloud provide in terms of content-based routing. So some of the routing is also like, we look at a specific field on a document and then route it to a specific core, and all documents that share that value route in that core. That's normally used for like customer-specific data. It's like a customer has, the document has like a customer ID, and so we route the document to that customer's core for them. We then batch documents together. We normally wait 5 minutes in batch for documents that have the same routing rules to be gathered together, mostly because Solr really prefers batch feeding. In our experimentations, we normally wanted about 50 documents per batch for Solr to be kind of optimally happy. We then send the batches to Solr, off they go. We send them off to a verify queue. The verify queue waits about 10 minutes. We auto-commit the Solr cores every 5 minutes. So it waits about 10 minutes, goes and checks to see if the batch successfully made it into Solr. It has no real, we specifically designed it so it has no real way to tell. We don't like go like scrape like Solr's like commit log and things like that. We just query for the document. If you find any of the documents, then that means the batch successfully updated. We use a timestamp to verify that it has actually been changed. And so if we verify the documents in place, we're good, we're totally done. If we have some kind of failure in any of these steps, especially in verify, we have a reprocessing step that will take the DIDs that failed and try to figure out why they failed and reprocess them. And then after a couple rounds of that, if we have not been able to reprocess them, we'll send them off to a dead queue in essence for investigation on like why it failed to search to an index. So all of our clusters are master slave today. And so we have a bunch of them, so you can imagine these are all master slave setup. So logically, the feeding platform knows where to route the documents based on our sharding stage, and we'll send them to the correct Solr masters, and then we make use of query load balancers across the slaves to retrieve them. So we'll talk a little bit about our setup in Cassandra. So we have 2 column families per pool, and pool is like a logical classification of documents. Customers come to us and say, hey, we want to make a new search application on top of your platform. Like, cool, we'll make you a pool. Right? It kind of isolates customers from each other. And so we have 2 column families per pool in Cassandra. We have an initial data pool, and then we have a translated pool. And we store both stages in Cassandra because having it translated also in Cassandra will allow us to do refeeds much more quickly. One of our primary use cases of refeed is when we upgrade all of our Solr boxes, right? So when we go from upgrade 500 Solr boxes, you don't want to go back and ask, 20 or 30 different customers, hey, could you go refeed your data from your data store? So we have this intermediate data store that allows us to then refeed those documents. Both column families have a document ID as the key, which is a unique identifier for the document that the customer gives us. We don't care about how the customer makes the decision, they just give it to us. The initial column family, it has both a key and then a number of fields based on the data. It's dynamic, right? So like, since you can tell us about, hey, this document has these fields, this document has a different set of fields, right? You have to both specify them on the insert and then their request back when we load it. But it allows you to make kind of whatever decisions you want, and Cassandra really easily supports that use case. And then the translated is much simpler. We just have a document ID, and then the single transform content field. We actually have 3, I should remember the 3rd. We also have a little bit of metadata around where the document was routed, so we can verify that the routing was correct, kind of after the feeding cycle. And so talking a little bit about how we read and write from Cassandra, we quorum read and write in all cases. And it's mostly because our feeding pipeline doesn't self-heal if a document failed to load successfully. So if we load an older version, we're actually totally screwed. There's nothing we can do today to recover it. Right? Because in essence, as far as we view the data, they're just streams coming in to us from customers. And they might be streams of jobs, streams of resumes, streams of user actions, streams of whatever. We don't really care. So because of that, we both quorum read and quorum write. So yeah. And Josh to talk a little bit about the actual servers we have set up.
So I'm the DBA for Cassandra. Luckily, Cassandra makes it really easy for DBAs. So I'm here to talk about our actual ring and a couple of problems that we had initially. We have numerous rings set up. We have a 3-node test ring, which is what they use to test new products. Then we have our 21-node production ring, which has 56 terabytes in it. We're running DataStax Cassandra, version 2.0.5. We are running virtual nodes, which are a godsend. All the tables are replication factor 3, and normally our average, we usually get about 4,000 writes per second and 3,000 reads per second on a usual day. So those super nodes they were talking about earlier, we have those. We're using Dell R620s with 120 gigs of RAM. These were actually given to us. But we have a 3x1 terabyte, 1.6 terabyte SSDs at RAID 5. SSDs actually were a godsend to us. So when I originally took over Cassandra, we were actually using version 1.0.8. And I've actually been the DBA for Cassandra for about 2 years now. So when I took it over, there's a lot of issues we had. We had issues with compaction, cold reads, and garbage collection. For compaction, like I said, we were running version 1.0.8. Originally, it was single-threaded compaction. And the compactions were ending up eating up the heap space until we ended up getting an out-of-memory error for Java. So it took us a little bit to fix that, or figure out what the problem was. So to fix it, we figured out JNA was not installed, so we installed that and enabled it. We reduced the mem table and cache size, which helped with the out of memory. And then the thing that just killed it was increasing the heap size to 12 gigs, because the out of memory would slowly eat up throughout the days and then finally shut down each Cassandra node. So throughout the ring of 21 nodes, 2 or 3 would go down each day. And then doing all this actually fixed the problem. So as Joe said, with the refeeding, we had a cold read problem. This was back when we were on spinning disks. So whenever they refeed, they take every single row inside of a queue and just push it through. So that means each row will be read multiple times. So that means SS tables that haven't been touched in a while, it has to go to disk to read them. So that means a lot of seeks, and spinning disks hate seeks. So the way we fixed that was throwing money at it and buying SSDs. We had the nightly repair times. When I took over, it was taking 23 hours per day to do a repair. And with the SSDs, we ended up going, once we switched our SSDs, repairs went down to 3 hours.
This was still on 108?
Yes. It decreased the write latency time from 15 milliseconds down to 2.4, which is, I think, higher than what we have now. I think we're down to like 2.2. But one thing I did notice when I went to SSDs, the Cassandra.yaml, changing the concurrent reads and concurrent writes, that was a big issue when we first switched over. I think it's defaulted to 32. And changing this actually fixed it to where we were actually getting the throughput that we needed. As Joe said, we're now in the process of moving to AWS. I'm in charge of moving that. So right now we're using a combination of AMIs already configured with Cassandra installed, and we're using Chef to configure the various like YAMLs and environments for each instance. So we can theoretically push out a new instance with a clickable button now, and it will automatically join the ring, and everything will be good. Right now we're using R3 extra larges with EBS optimized. Originally we were using ephemeral storage. We had an issue with Amazon. We had a six ring cluster, and Amazon decided to decommission 4 out of the 6, and it dropped everything. So that's why we went to EBS optimized. So far we haven't really done it at high volume, but the performance seems comparable to local data center. It has 30 gigabytes of RAM. The key issues were making sure I got provisioned IOPS and using the EBS optimized. Without those two, EBS definitely would not be able to be used. So we use two availability zones to make sure high availability, and as Joe said, we use quorum reads and writes. And we are currently deploying version 2.0.12. Any questions?